Okay, grade 12, I am Natasha Barton. Today we're going to go through a few helpful exam tips, how to prepare for your exams and all of that. Okay, so firstly, I just want to remind you guys of the topics that you have to study for paper 1. Okay, you guys are familiar with this. You just studied for your trial exams, but there are some things that I just want to point out that I did mention on yesterday. Was yesterday Sunday? Yes, yesterday. So when it comes to the mechanics, Newton 1, 2, 3, universal law of gravitation, right? When it comes to momentum and impulse, vertical projectile motion, work, energy, and power, you guys must please remember that all of these topics deal with vectors. And when you're dealing with vectors, it means direction is important. In this previous exam, so this trial exam that you guys wrote, fortunately, none of the answers actually required the direction. So if you didn't write down the direction, they didn't give a mark for it, but they were supposed to. So in your final exams, they're going to be more strict. We normally say don't use the Gauteng exams as a guide because they're a little bit easier. Rather go and look at, for example, the Western Cape's exams, Eastern Cape, Limpopo exams are also very, very good. I'm not trying to shame any province, but there are some provinces that are better than others. Okay, so when you get into your exam, what I want you guys to do from now on is, remember Newton's laws is normally question number 2. Momentum and impulse, we're somewhere around question number 3 and so on and so forth. When you open up your paper, go to these questions and go and write down vectors. In that way, you're going to make sure that when you substitute into the formulas, you remember direction, and when you get your answer, you remember direction as well, because that tends to be a problem. Some of you, when you were using or substituting into vertical projectile motion, you left out your directions, and therefore your answers were incorrect. Are we okay? All right, so go and do that. Doppler effect, don't neglect redshifts. Normally it's few marks, but sometimes they can go and change the whole scenario and make it evolve around light. So make sure you're familiar with your redshifts. Electrostatics, I could tell that not all of my learners went and watched the videos on electrostatics. It's an important section of work, and those videos I think do explain very, very well. So go to the Junior Turkey website, or if you don't want to go and register on the website, I recommend that you go and register. But if you don't, go onto the YouTube channel. I've linked that chapter, right? And go and watch the videos on electrostatics. Find some time and just go get it done, then it's out the way. When you're busy with this section, direction is a big problem, but I'm going to go through that just now. Electric circuits, I found is a big, big problem, but we're going to go through that today. Electrodynamics and alternating current. Guys, this is your free marks, so make sure that you master it. And then when it comes to matter and materials, atomic spectra, so that is where, for example, I tell you we have an electron, it's in the ground or on the ground state. We shine light of a suitable frequency onto it, and then it goes from the ground state to, let's say, energy level 1. In one of the provinces, I don't know which one, they actually did the whole photoelectric effect question on this stuff. So there were a lot of learners who didn't focus on atomic spectra, and therefore they really struggled with this. So don't neglect anything. You guys have time. Plan well. Make sure that you use the time available to you. Count the number of topics and say to yourself, today I'm going to cover this topic, the next day the next one, and so on and so forth. Brains are different, the way you remember things are different. When I was in high school, one of my friends could read and would remember. I couldn't do that. I had to make 100 notes over and over and over again until my hand felt broken. If you need to make the notes, you make the notes. That's how you work, okay? But go and count the number of topics, alternate between your subjects, try to do a little bit every single day, and try to keep your memory or keep refreshing your memory, because if you keep reminding your brain that you need to hang on to this, you won't forget it. But if the last time you studied this work was in your trial exams and 2 days before you open up your physics books, you're going to forget the work, okay? So try to find ways to remember it. Are we okay, guys? You guys are very quiet. Okay. Now you're going to see that I summarized everything. On your Newton's laws page, I'm just going to run through some of the points. Again, some of you are familiar with this because I did go through it a bit yesterday, but I'm going to go through it in a bit more detail now. So when it comes to your normal force, please remember your normal force is perpendicular to the surface. But in this case, if you have a block on an incline and there is a force pulling up on the block, like in this case, remember your normal force is not going to be equal to the weight. Normal force is only equal to the weight if the only vertical forces are the normal force and the weight. Then they equal and opposite. But in this case, think about it. Here's my box. If I attach a rope and I pull up, what I'm doing is I'm sort of lifting the box off of the surface so that it doesn't press into the surface as much. Normal force is what you get because the box is pressing down onto the surface. So if you have a force that is pulling up, is the normal force going to increase or decrease? It's going to decrease. Okay, think about between the surface. There are documents over there between those learners over there. You can take it back. Okay, if you pull up on the block, it's not going to press as hard down onto the surface. So if the force is up, the normal force is going to be smaller than the weight. And in this case, we can say the normal force is equal to the weight minus the y component of the applied force. If we're on an incline, remember, weight is always straight down. Remember I told you guys what my lecturer said, spit onto the board and the spit's going to run down the board, right? So in this case, the normal force is not equal to the weight. Instead, the normal force is equal to the component of the weight. Don't forget these things. You guys tend to forget them when you're tired or panicked or stressed or in a trial exam, okay? So in your trial exam, there was an important question. I'm going to change the scenario now. In your trial exam, we had 2 blocks. And what they did is they said that this block on the right-hand side, I'm going to call it block B, is being pulled at an angle like that. I'm going to change it now. And I'm going to say instead, block B is being pushed at an angle. Okay, just to make you guys think a bit more. Now they said to you, block A and B are made up of exactly the same material. They're on exactly the same surface. And then they said to you, why is it that the friction force experienced by this block is different from the one experienced by that block? I don't think there was any learner who got full marks for that question. So in the future, this is what I want you guys to do. Number 1, you're going to answer using bullet points. No matter what, if you have an explanation, you answer using bullet points. Never think you can answer with a paragraph. A paragraph makes you think you're doing a lot of work, but then you don't write down any valid points. And then you guys are going to think in this way: controlled variable, independent variable, dependent variable. This is science, okay? I've never actually mentioned this to you guys before, but it's still exactly the same. The same way you think in your practical is the same way you're going to think in your exam. So let's think about this. They asked about the friction force. On your notes, you're going to see here, I mentioned, this is taken from your exam guidelines. Remember, the friction force is proportional to the normal force. It's independent of the area of contact, and it's independent of the velocity of motion if the object is in motion. So I want to elaborate on this. If you have this block that you see on my table, it's currently made up of cardboard. And then we take this and we cover it with exactly the same cardboard. We put it on the table as well, and we push them. Please understand, this block does not experience more friction because it's bigger, okay, or because it has a bigger surface area. Surface area does not affect friction. You guys hear me? Doesn't matter how wide it is or how flat it is, that's not going to affect friction. Friction is dependent on the type of material. Type of material is in the formulae. Here are the formulae for friction. Type of material is what you get from your coefficients, either your coefficient of kinetic friction or static friction. This coefficient takes into consideration what materials are rubbing over each other. Is it cardboard and plastic? Is it cardboard and carpet? What are those materials? That is that part of the formula. The only other thing included in this formula is the normal force. So the only 2 things that your friction force is dependent on is the normal force and the type of material, not the surface area. That said, this is how we're going to answer a question like this one. And you all see that the applied force is pushing onto the block. Everybody see that? If I break it up into its components, there's going to be, well, depending on where the x is, I think let's put the x over here where you guys are familiar with it. So if there's my x, the components is going to be one straight down, that's Fy, and then there's going to be one to the right, that is Fx. Which one of these components is responsible for pushing the block into the surface? The y component, right? It's the y component. This one over here is responsible. It's pushing down. Now, if it is pushing down, does the surface have to press up more or does it have to press up less? More. Okay, so think about it. Now the surface is doing a lot of, I'm not going to use the term work, but it's doing a lot of work to make sure that the block doesn't fall into the earth. Okay, so in this case, if we want to explain why it is that the friction force on this block is larger than the friction force on that block, number one, we're going to say both of the blocks are on the same surfaces, and therefore the coefficients in this case of kinetic friction are the same. I didn't say this is the controlled variable, but for stating this, which I think very few learners did, you actually get 1 mark. You stated your control. Now that we're done stating the control, we think, what did we change? So look at these two blocks. What's different for the two blocks? What has this block B got on it that A doesn't have? The applied force. That is what is different. So now we're going to mention that this block, block B, has the force at an angle on it. You don't have to mention it in so many words. But what does this force do? It increases the normal force. Now we are mentioning something that friction is dependent on. What are we changing when we apply that force? We are changing the normal force. That is our independent variable. Specifically, we mentioned that we are increasing the normal force. Now, since in the formula we can see that friction, whether it be kinetic or static, is proportional, directly proportional to the normal force, we're going to say friction is directly proportional to the normal force. Therefore, as the normal force increases, the friction force increases. So you get 1 mark. Your second mark is for saying that the normal force increases because of the applied force, and 1 mark for stating that these two are directly proportional, and therefore as the one increases, the other one increases. Okay, this over here, controlled variable, independent variable, dependent variable. You can never say too much, but you can say a lot of nonsense, okay? And that often happens. I was a learner who was responsible for that. You write down the whole essay and then you think, oh, I did it. But you haven't written down anything worth the mark as well. Something else that you guys must be careful of. I found a lot of learners using shorthand notation. So instead of just saying this, which the marker should mark correct, rather try to write out directly proportional. Try to use your words. Let's put it that way. Don't just use shorthand, but make sure that you write down the points that are worth the mark as well. You don't need to write a lot. You just need to write things that count. Does that make sense, guys? Are there any questions at this point? Okay. Gravitational force. Over here, I've included this formula over here. I'm not going to go and elaborate on the formula like I did yesterday. It wasn't necessary. But remember, this formula you can actually obtain by taking this one and equating it to that one. This is the formula that we use. Let's say that we're on a planet. Let's say here's Mars. And I say to you that there's an object on Mars. Then I ask you, what is the gravitational acceleration on Mars? Let's start off with Earth. What is the gravitational acceleration on Earth? 9.8 meters per second squared. Don't forget your square. Now on Mars, since the planet is bigger, I think it is, or is it smaller? Smaller, since the planet is smaller, right? We know that the gravitational acceleration is going to be different. And because of that, we can go and calculate the gravitational acceleration. G is a constant from your table of constants. Don't neglect your table of constants. In your table of constants, guys, you have the mass of the Earth. You have the radius of the Earth. You have the mass of an electron. There are a lot of things in that table. Go and look at that table and familiarize yourselves with it. I was one of those learners who did not realize that table existed. And from grade 10 to grade 11, I didn't know where to find information. So don't neglect that table. But if we're trying to find the gravitational acceleration of Mars, we're going to take G, which is a constant, the mass of Mars, the radius of Mars, and that is going to give us the gravitational acceleration on that planet. Are we happy? Okay. Then we have Newton's first law. If ever you have an object that is at rest or constant velocity, you guys must not forget that the net force is going to be 0. But don't start off by just saying F net equals 0. Start off by saying F net is equal to MA and then substitute into it the 0. Because what you're doing is you're confirming that you know Newton's second law, but Newton's second law goes back to the first law, because if an object is at constant velocity or rest, the acceleration is 0. You're showing the marker that you know this. Okay, we don't write down nonsense, but we write down enough to make sure that we always get our marks. Are we okay? Alright, then over here we have Newton's second law. This one you guys are very, very familiar with. What I want to emphasize to you guys, and I won't do it throughout this session, but please create links between the definitions, especially long statements like this, and the actual formulae. So you guys are familiar with Newton's second law. I know all of you know it off by heart, because if this was asked in any trial exam test, my learners know this definition. But a lot of you learned it by cramming it. You don't have to cram. Here's the formula. If we divide both sides by mass, we have F net divided by M. What does Newton's second law say? It says when a net force acts on an object, the object will accelerate. Okay? The acceleration is directly proportional to the force. In other words, as the force increases, the acceleration is going to increase. When the force is 0, the acceleration is 0. And this formula or statement also says it's inversely proportional to the mass of the object. In other words, as the mass increases, can you see it in the denominator? If you put a big number in a denominator, the output is a small number. So therefore, that decreases. All of this comes from formulae. So try to use the formula on the side. Don't just assume that you can just copy the formula, because sometimes you guys do that and just write down what you see in the formula. But try to use this so that if you forget, you can go to your formula sheet and use it to refresh your memory. Are we okay? Are there any questions? Okay, then Newton's third law. This law, more often than not, is going to be tested in the section on universal gravitation and in electrostatics. Okay, we like to do this. We say to you guys, there are two charges. Over here we're going to have a charge of positive 100 coulomb. Over here we have negative 10 coulomb. And then I say to you, this is A, that is B. I tell you that A is exerting a force on B. It's an attractive force. And then I ask you, how does the force that B exerts on A compare? And most of the time you guys say, well, because this one's small, it must be exerting a smaller force. But that's not true. Newton's second law says, if object A applies a force on B, then object B will apply an equal but opposite force on A. Which makes sense, because if you calculate this, you're going to say F equals K QA QB divided by R squared. Over here, you're going to say F equals K QB QA divided by R squared. It's exactly the same. Multiply together, you're going to get the same answers. So please, when it comes to Newton's third law, watch out for it in sections on electrostatics and Newton's law of universal gravitation. Mm. Yes. So you mean like just in a normal, like you have two boxes that hit each other? Yeah, so even if you have two boxes, so you have a 1 kilogram box and then you have a 1000 kilogram box, right? In this case, when this one hits that one, the 1000 kilogram one is going to hit back with an equal but opposite force. Okay, I think, yeah, okay, so I'm gonna leave it there before I over explain. Newton's law of universal gravitation, I think, is an easy one to use. The only mistake you guys sometimes make is sometimes they only give you the distance between the two planets. Remember, the distance is the distance between the centers. So if they only give you the distance between the planets, remember R at the bottom is going to be from there to there, from there to there. Remember to add on the radiuses, or radii, sorry, as well. Okay, don't forget those things. We fine? Not fine. Okay, let me give you an example. I know that I have something over here. I think this was a question. I don't know if I asked it to you guys or if it was this year's group. But let's quickly see. Grade 11. I think it's over here. Let's just find it. Here's the problem. So in this problem, can you see we have Jupiter and we have Earth? So one of the questions says, calculate the gravitational force that, over here, the magnitude of the gravitational force that Jupiter exerts on Earth. Okay, now to calculate that, we need the mass of the Earth, the mass of Jupiter, and then we need the distance between their centers squared. So how I got this number over there is, I said, this is from the surface to the surface, but I need the distance from the center to the center. So in the question, they gave us the radius of Jupiter. On your formula sheet, in the table of constants, you get the radius of the Earth. So I said the radius of Jupiter plus this 5,88 times 10 to the power of 9 plus the radius of Earth. And that's what I plugged in the place of R. Is that fine? Also, guys, don't forget to square. I always forget. You guys sometimes forget. Don't be like me. Remember to square. When you go back and you go and check all of your answers, go and check specifically. In the section on the gravitational law, the second section on electrostatics, did you go and square the distance between the two objects? Are we okay? Okay. Then we can go back to grade 12. Okay. I'm now going to go on to momentum and impulse, and I'm going to put together the theory. Once I'm done getting together all the theory, so we'll probably take about an hour, right, to just get through the theory. Once I'm done with that, we're going to look at specific problems. So I first want to point out the mistakes you guys make. I want to create links between the things, and then we're going to look at problems. I've printed out big documents for you guys, so we'll look at that in a moment. Okay, momentum and impulse should be an easy section, but it's not always an easy section. If you struggle with this section, I've created videos for Junior Techie. They should be uploaded, let's say, in the next week. So once they are uploaded, I'll send the link to you guys. But I think it's the same one I uploaded onto Google Classroom. So go and watch that. Go and make use of the videos. Okay. In this section, you open up your question. What's the first thing you're going to write down? Vector. You're going to remember that this section deals with vectors. This is the biggest mistake my class always makes. Momentum and impulse, we forget about the vectors. Okay, so don't forget, whenever you substitute here, the V is velocity, the F is force, and they are vectors. Okay, now momentum, you guys know the formula. When you guys are panicked, for some reason you go and do this. I see it all the time. Or you leave out the half and you just say mv squared. With the half, what formula is this? Kinetic energy. It happens a lot when you guys are stressed. So please don't confuse momentum, mv, with kinetic energy. Go and look at your formula sheet. It's on your formula sheet, okay? If you're someone who gets anxious, if you're someone who gets panicked, go and take a look at your formula sheet. It's going to guide you. That's why it's there. You can go and tear it off. So please, in your exam, You guys are now going to get exam booklets, not the ones that I give you, but the actual like answer booklets. Do not tear pages from there. No matter what, you do not tear pages from your answer booklet. If you do so, you're not going to get your matric certificate at the end of the year. Okay? If you make a mistake, you cross it out and you try again. Okay? But don't tear out pages. However, the question booklet is going to be similar to the one you got for your trials. You guys all saw the formula sheets at the back. You can actually tear that off. Okay, you're not going to get into trouble if you tear that off. They stay with the school. So once you guys are done writing, Mr. Miller gives it to me, and I keep it in the storeroom, and I give it to the other learners, or they just accumulate dust. Okay, in my school, when we were done with our exams, they actually just gave us our papers, the question paper. So you can tear off the formula sheet. You're welcome to do so. Just do not tear pages from your answer booklet, please. Okay. So on your formula sheet as well, you're going to see how you can calculate change in momentum. This doesn't happen often, but you guys might remember in class, we did a small section where I showed you how we add together vectors in this section. Maybe. It's right in the beginning of momentum. Remember, change in momentum is equal to P final minus P initial. If I'm going too fast, you guys slow me down. If I say to you, we have an object, the object is moving in this direction, and then suddenly it's going to maybe turn around and it's going to move in that direction. What's going to happen is in the beginning, it's going to have a certain momentum to the right. In the end, it's going to have a certain momentum to the left. If I ask you to use vectors to show how you can add these momenta, I think, together, right? You don't say P initial plus P final. Never P initial plus P final. It's P initial plus the change gives us the resultant, which is the final momentum. Does that make sense? All that I did is I took this formula and I manipulated it. I put the P initial on the left and I got P final is the initial plus the change. Okay. Doesn't happen often, but I've seen it in a past paper. So in this specific case where we have the momentum changing like I'm showing on the board, your diagram is going to look something like this. You're going to start off by drawing your diagram for the initial momentum or your vector, your arrow. I saw some of you use arrows like this. Please don't do that. It's a very confusing arrow. It makes it difficult to mark sometimes. So don't use that arrow, use sharp arrows, better than my one. That is your initial. Now, if we are doing vector addition, remember I taught you guys two types of vector addition. The first type is your parallelogram method or your tail-to-tail method, where you attach them tail to tail, then you complete the parallelogram, and then you draw in your vector. The second one, the most important one, is the tail-to-head method. Forget about the parallelogram method. You guys focus on the tail-to-head method. Tail-to-head method says we add vectors by attaching the tail of the next one to the head of the last one. So in this case, to the initial momentum, we must now go and add the change in momentum, because remember, we are adding these two together. We're adding the initial plus the change. Then when we're done adding together the vectors, then we say, draw in the resultant vector. P final is the resultant vector. Okay, it's what results when the initial momentum has the change added onto it. So based on that, to draw P final, we don't now go to this one and add it onto the change. Now we say, where is the tail of the first vector? Here it is. Where's the head of the last vector? There it is. The resultant is always from the tail of the first to the head of the last, and that is the final momentum. Okay, don't forget tail to head, tail to head, tail to head, but resultant, tail of the first to head of the last. They do ask for this, not very often, but it might be the difference between the mark you want and the other mark. Are there any questions? Yeah. All right, next we have Newton's second law of motion in terms of momentum. It's an important law. I gave this to you guys already. I said if you have airbags, seat belts, rester beds, okay, that is what we use for trucks. and they say to you that, for example, what is the reason or purpose of the airbag? An airbag is there so that you undergo the same change in momentum. You're going from 100 kilometers per hour to 0. So the change in momentum is the same. You're going from 100 to 0. Whether you do it in 1 second or 2 hours, you're going from 100 to 0. Okay, you need to come to a stop. So we say the reason why there are airbags is because for the same change in momentum, same number, if you go and you increase the time over a longer period of time, what's going to happen? If the change in momentum is constant, let's say it's a number like 5. First we were dividing 5 by 2,5. Now instead of 2,5, we divide by 10, right? When you say 5 divided by 2,5, what's the answer going to be? 2. Now we say, no, we're going to increase the time. Now we're going to say 5 because momentum is constant divided by 10. What's the answer going to be now? 0,5. Am I right? A half. Okay. So as you can see, for the same momentum, when we increase the time, the net force decreases. Okay. So whenever they ask you guys to mention why we are changing the time as we do, or why we use seatbelts, or why we use airbags in terms of momentum, for the same change in momentum over a longer period of time, we have a smaller net force and therefore less impact. Again, look, controlled variable, same change in momentum. Independent variable, longer period of time. Dependent variable, smaller net force and therefore less injury. We've mentioned all 3 points. We're going to get our 3 marks. You don't need to write an essay. Just make sure that you mention all of the points. Any questions? I can see you guys are getting tired. Just stay with me. Okay. Now, after that, we changed the formula and we have impulse. I saw in the June exam, a lot of you did not study your impulse. Go and revise impulse. It's very important. It's linked to momentum, and sometimes the questions are easier, but only if you remember the questions. If you are given a graph of net force versus change in time, like the one in your textbook that looks like this, they ask you for momentum. Remember, you calculate momentum from the graph by calculating the area under the graph. Okay? A big mistake you guys made in your paper 1. They said in the section on electric circuits, use the graph to determine the EMF. They also said use the graph to determine the internal resistance. Most of you used formulas and you didn't get your marks. They are very, very strict. When they say use a graph, they mean use either the gradient or make use of the y or x intercept. Don't forget that. Mathematics is the language through which we communicate physics. Okay, chemistry as well, but math is a language. Just like English is a language, math is the language through which we communicate physics. So if we say use the graph, we're checking to see, do you know that there's a relationship between gradient and a physical quantity? Do you know that there's a relationship between the y-intercept and an actual physical quantity? So please pay attention to words like that, using the graph. Impulse momentum theorem, you guys I think are okay with using that one. Principle of conservation of linear momentum, we're okay. Except when you guys go and do that weird thing and you use the kinetic energy formula instead, or you forget they are vectors and you don't substitute your direction. Okay, very often you guys don't sub your directions in. Last thing I'm going to mention in this topic is when you have or asked to prove whether a collision is elastic or inelastic, don't start off with this statement. You guys are actually okay with it now. This is a better group. You first calculate the sum of the kinetic energy before. So the kinetic energy for object A plus the kinetic energy of object B before the collision. Then you calculate the kinetic energy after. So the kinetic energy of object A plus B after the collision. You see, are they equal? If they are, you say they equal, therefore it's elastic. If they're not equal, you say, therefore they are not equal, therefore it's inelastic. But you do not start off with this statement, please. That is the wrong statement to begin with. We happy? And this formula over here we will come to in a moment. Isolated system. Isolated system is a system on which the net external force is 0. In other words, there are two objects that are going to collide. What forces are we interested in? The forces they exert on each other. We don't want friction to get into the way. We don't want air resistance to get in the way. We're not interested in those things. Those are external forces. Internal forces is the forces between the two objects that we are interested in. Does that make sense? Make sure that you know how to define an isolated system. It is important. It comes up very often. I asked this yesterday. Does a collision need to be elastic in order for the principle of conservation of linear momentum to hold? No. Whether the collision is elastic or not, doesn't matter if it's elastic or not, you can still use this formula, okay? Comes up a lot in the multiple choice, and most of you get it wrong. If they ask for a connection between linear momentum and elastic and inelastic collisions, you sort of deal with it as if there isn't one. They're both collisions, but you don't need the collision to be elastic for linear momentum to be conserved. Any questions? Are we okay? Okay, we still have 20 minutes left. Stay with me, guys. If you need to stand up, stand up. Okay, vertical projectile motion. It went better than it could have, but it didn't go as great as it should have. First mistake a lot of you made, projectile versus free fall. When you define free fall, we say it's an object that only has the gravitational force on it. A projectile is being projected into the air. So it begins with an initial velocity and then only has the gravitational force on it. You get 1 mark for this part, 1 mark for that part. So you didn't lose all your marks, but you got 1 of the 2 marks if you did not mention initial velocity. Okay, now this diagram here has nothing to do with those at the bottom. The links at the top are not the same as the ones at the bottom. Please create a distinction. In all of these equations of motion, everything is a vector. This is velocity, the final velocity. This is the initial velocity. This is acceleration. The only thing that is not a vector, the only thing for which you do not substitute a negative or positive in, is the time. Okay, so all quantities are vectors except time. Don't make the mistake of forgetting this, or you're not going to get your marks because your answers are definitely going to be wrong. We're dealing with vectors here. Another mistake I saw, guys, we're dealing in the y direction, not the x direction. Do not copy down the x formulas. I did not penalize you guys if you use the x formulas, but this is vertical projectile motion. So you guys must use y, not x. You're welcome to use a g instead of an a, but a y, please, not an x. We happy? Okay, now over here. Time symmetry, speed symmetry, I think you guys remember. The time taken from here to here is the same as the time taken from there to there. Time from here to here, same as the time from there to there. Time from here to there, same as the time from there to there. The speed here is equal to the speed there. Are the velocities equal? No, why? Direction. Okay, it's because of direction. If the negatives and positives are there, they're not equal. Negative is not equal to positive. So this one is down, that one is up. So the speeds are equal, not the velocities. Speed here is equal to the speed there. Now here's something you guys mess up on. At C, what is the speed going to be? The speed at the top, at the maximum height, is always 0. You see, at the maximum height, the speed is 0. Okay, it's not the max speed. I guess I shouldn't write down that, but there. What is the acceleration going to be at the top when the speed is 0? 9,8 meters per second squared. It does not matter that this object has come to a stop. The earth is still working on it. The earth is still pulling it down. That is why it came to a stop. So even right here at the top, A is still going to be equal to g. Don't forget that. We okay? Yeah, I know you guys are getting tired, but we're almost there. Okay. So I've mentioned a whole lot of details here about the diagram on the right hand side. Read through them, make sure that you understand them. Remember that when an object hits the ground, its velocity is not zero. If its velocity was zero, then if I dropped a steel ball from the sky, right, you would be willing to stand underneath it as it falls down. But you're not willing to do so because you know when it hits your head, its velocity is not zero. It's going to hit you very hard. Okay, don't forget, here at the bottom, the velocity is not zero. The velocity is at a maximum, depending on where it is, of course. But normally, here, the velocity is at a maximum, not zero. So we're not talking about the ball hits the ground and comes to a stop. We're talking about the ball just hits the ground. Okay, just hits your head. Think about it that way. These graphs of motion tend to be a big problem. I'm not going to spend a lot of time on explaining this right now, but in this case, remember you can walk a position time graph. If the ball goes up and goes down, the position time graph looks similar. We can rotate it, but it looks similar. Looking at this graph over here, where is our 0 point? So comparing this graph to this, where is the 0 point? Is it at her feet? Is it at her head? Is it in the sky? Where's 0? No, for this position time graph. Where she threw it up, that is our reference point. Okay. If they say the ground is the reference point, which they sometimes do, this graph is going to change. Same shape, but now it's going to look like that. You see, now it goes or starts above the ground, which is the 0 point, and it stops on the ground, which is the 0 point. Take into consideration the reference points when they give it to you. We look at a velocity time graph. What does this point over here correspond with on this? Is it A, B, C, or D? What is that point? Okay, I heard C's, I heard B's. The correct answer is, read the graph. Here we have y values, positive y values. Here we have y values, negative y values. What will the y value be here? 0. Where along the motion is the velocity 0? At the top, over there, at B. Oh. Excuse me. Okay, my voice just went, it happened. So over here at this point, I don't know. It just went. You're going to read the graph. It will come back eventually. You're going to read the graph. Maybe it's from my whiteboard, the chemicals. When you guys weren't here, we smelled a smell. I don't know if that's right, but we thought it was chemicals. It's a new whiteboard. It smells horrible. Or screen. So anyway, this point over there corresponds with that point because we know right at the top of the motion, the velocity is 0. Read the numbers on your velocity time graph so that you understand it. Don't just look at the shapes. I don't know why, but in grade 10, we developed this habit of looking at the shapes. Read it. You can see over here, there's 0. It's going away because the numbers increase. Here we have a big number and it's becoming smaller and smaller and smaller, but it's still positive. It is slowing down. That is what we see. Because we're going from a number like 20 to a number like 0. Okay, over here, along this motion, we're going from 0 to a negative 40, for example. 0 to 40, if we are driving, that is speeding up. So make sure that you read the numbers. The gradient of this graph is acceleration. The area under the graph is going to give you either the displacement, if you take direction into consideration, or it's going to give you the distance if you just add the numbers together. Area under the graph is going to be this triangle and that triangle. It's between the actual curve and the x-axis. And lastly, in your section, acceleration is always 9,8. If you chose down to be negative, be consistent, it's going to be at the bottom. If you chose down to be positive, it's going to be at the top, right? But it's just 9,8. That is vertical projectile motion. The biggest mistake that we make, that I've seen you guys make, is this part. Okay. All right, work, energy, power. This one is a problem, but it's not necessarily because it's difficult. Because you guys want to get it right the first time. Don't try to get it right the first time. There are so many different formulas that sometimes the first formula you use is not going to be the right one. There's no need to panic if the first formula is the wrong one. It happens to us as teachers all the time. It's going to happen to you. Physics, science is trial and error. Start off with one, see if it works. If it doesn't work, move on. So we know work is equal to the force multiplied by the displacement. But these are magnitudes only. You don't take direction into consideration. If you are busy with a problem like this, I suggest drawing on your question paper a free body diagram. Let's say the object is moving that way, but the displacement is that way. Go and draw it in on your question paper where the marker can't see, so that you can see the angle between the forces and plug it in correctly, the force and the displacement. Go and do that. It's allowed for you, not for the marker, but for you. Go do what you need to do. Net work, remember work is measured in joules. It's a scalar quantity, no vectors. So in this case over here, the net work we're going to plug in as a scalar, just the magnitude. Displacement, just the scalar, etc. We can also calculate the net work by adding together all of the works, or we can say it's equal to the work done by the conservative forces plus the non-conservative forces. Alright, mechanical energy. You get different types of energy. You get light, you get heat, you get chemical energy, all of those different things. Mechanical energy is the sum of the kinetic energy and the gravitational potential energy. This formula is a formula for scalar quantity. So this is not velocity, it's speed. But if you put in a negative, it's not going to change anything because there's a square. Over here, this g is not the vector, it's just the scalar, the 9,8. Don't go and get confused, panic, and put negatives over here. So I guess this is the one section, your work, energy, and power, is the one where you're dealing with scalars most of the time. There are some vectors, but here you have scalars. Okay? Mechanical energy is the sum of the two energies. So that brings us to the principle of conservation of mechanical energy. You only use this principle when there's no friction, no non-conservative forces. So two cases is you have an object and it is falling through the sky. It's in free fall. That's the first case. On this object, what force do we have acting? Gravitational force. Gravitational force is a conservative force. Okay, no non-conservative forces. The second case where you're going to apply this is where you have a pendulum. So you have a ball attached to an inextensible light string. It's going to be swinging around. It goes from a maximum height to the bottom on the ground. Over here as well, you can apply this, but you can't apply it anywhere. Make sure you only apply it in cases where the only forces acting is conservative forces. An isolated system is one where there are no non-conservative forces in this specific case. So we say a system is isolated when the net force, excluding gravitational force, is 0. And this over here you guys can make use of or just ignore. Okay, I have the definitions of conservative and non-conservative forces. Learn the definitions. But a conservative force is one that conserves the mechanical energy. No mechanical energy is lost in the form of heat, in the form of sound, in the form of light. Non-conservative forces are wasteful forces. Friction is a wasteful force. You go and you push a box. What does friction do? It slows it down. It takes your energy that you put into the box and puts it to waste. Those are non-conservative forces. An applied force is also considered a non-conservative force. Most forces are non-conservative forces except Fg. Fg, the elastic force of the spring, and the electrostatic force. But in this section, the only conservative force you're going to be dealing with is Fg. So you know you can use this formula, your conservation of mechanical energy, when the only force acting is the gravitational force. That's the only force doing work. Then we have the work energy theorem, which you can expand. You have the work energy theorem in general. If you have two non-conservative forces, let's say there's an applied force and friction, you're going to add together the non-conservative forces. It's not only one. In most cases, there is only one. It's normally just the friction force. But if you have two, you're going to have to add them together and plug them in there. I think it was in this past trial exam where this mistake was made. They weren't added together. So check to see how many non-conservative forces do I have and add them all together over there. Lastly, we have power. I think we're all okay with power. Just don't forget this formula if you have the average speed. Okay, very quickly. So we have 5 minutes left, it seems. The Doppler effect. You guys are really good at the Doppler effect. I'm very happy with that. Remember, Doppler effect speaks of pitch, not loudness. We say when something speeds towards you, its sound becomes squeakier. Not louder, it's going to get louder, but it becomes squeakier. That's the Doppler effect. As it moves away from you, its sound becomes deeper. Okay, that is the Doppler effect. Loudness is going to happen. Someone walks away from you, they're going to sound softer. But if they're moving at a relatively fast speed, then we're going to see the pitch changes. That is what the Doppler effect is about. In this formula, you guys know we're not plugging in negatives and positives. These are just the speeds. Okay, so these VL, VS, it's just speed values. Don't forget these formulae from grade 10. They're still useful. But I would just like to point out over here that this is an easier way for you guys to remember how to choose the positive and negative. When families, when people move closer together, when relationships become nicer and stronger because they move towards each other, it's a positive thing. So when it comes to your Doppler effect, you choose positive at the top when objects are moving towards each other. Whether it's the listener moving towards the observer or the observer moving towards the listener, when people, objects, things move closer together, we're going to say that's a positive thing. So positive at the top. When they move away from each other and relationships break and we no longer speak to our parents and no longer speak to our friends and things are just sad and horrible, it's a negative thing. So negative at the top, positive at the bottom. Are we okay? Don't work with this alone. Always use your logic, always use mathematics, but you can always use this to test to see if you're on the right track. Applications. They can ask about this for 2 marks, okay? So make sure that you can explain how a blood flow meter works, how they measure a fetal heartbeat using the Doppler effect, how ultrasound machines work. A radar speed trapping device is just like your speed trap. You know, the cars are driving. That makes use of the Doppler effect. Astronomy, here we're speaking about red and blue shifts. There is no reason, grade 12s, for you guys to mess up your red and blue shifts. You just need to study it and make sure that you understand it. But a mistake you guys make is they speak to you in terms of wavelength. You understand it in terms of frequency, and then you mess up the whole problem. What is the relationship between wavelength and frequency? Are they directly proportional? Are they inversely proportional? What's the relationship? Inversely. If they tell you you have a big wavelength, it means the frequency is small. They say you have a small wavelength, it means the frequency is big. Red light has a large wavelength. It has a small frequency. Blue light has a small wavelength. It has a large frequency. That is the relationship between wavelength and frequency. And in multiple choice questions, in long Doppler effect questions, make sure you identify what they are asking you about. Make sure you are alert, and that is why you guys must sleep before your exams, okay? I know sometimes it's stressful and you dream physics. I know that happens, but you need to get sleep. All right. That's why it's important that you guys study in advance. That while everyone else is panicked, you know, I did this, and you can actually sleep. Now that you guys have the time, don't rest just yet. You rest the night before your exam. It's a good feeling. I'm telling you guys, when everybody else is still studying, you switch off the light and you say good night. It's really, very nice. 8 o'clock and you're in bed. It's very, very nice. Okay. So study now and you'll enjoy later. Okay. Red shift, blue shift, there we go. When they give you guys diagrams like this, and you see violet, for example, red or blue, if we go from the lab, normally at rest is in the lab. We do measurements in the lab on the gases. And then they say a distant star gives this one. You check to see, does it move towards the red side, like in this case? If it does, it's a red shift. You check to see, here is the diagram at rest or in the lab. You check to see, do those dark lines move towards the blue side? Not left or right, the blue side or the red side. Okay, because they can switch them around. If it moves towards the blue side, you know that it is a blue shift. Okay, if you look at this diagram, you can see, as it moves towards, what happens is the waves are squashed together. Squashed waves means a shorter wavelength. Wavelength is measured from this point to that point. That's short, but the frequency is big. The red light, here's the wavelength. It's a long wavelength, but the frequency is smaller. Those waves pass you less frequently per second. That's what we're saying.